putting. Okay. Now here, look at this. This is our math. Here we have to find out the logical effort or all the other things in this math. But before going there, okay, this is the solution. So what you have to do? Before going there, I am going to write some formulas, okay? Here. I'm going to write some formulas. At first, you have to find out B. B is the branching effort. B is equal to B1 into B2 into B3 and dot, dot, dot. That means all the branches will be multiplied. That is the capital B. Then you have G. G is the logical effort. G will be small g1, g2, g3, g4, and others, dot, dot, dot. Okay, this is the formula. That means all the small g will be multiplied and it will give you a capital G. Then you have H. You can write E as well. You can write E. If you want, you can write E. This is electrical effort. So how can you find out this? You can find out C out. That means the extreme capacitor output capacitance divided by input capacitance. Okay. Now, then you can find out F. The formula of F is the multiplication of B, G, and H. Okay, BGH. All the BGH, you can find that. Now find the small f. Small f is the stage effort. Now here you can find out the small f by giving a power on top of this is n. Okay. So f to the power 1 by n. Remember, it is not f. No. This is not these. Do not write these. Okay, this is actually division, not power. So people make this mistake. They actually, in the calculator, they give a bracket, they write f, they write 1 by n. But that actually division. Remember, these will go up, right?
Yes, sir.
This is the power. Now, this is your f. What about P? Then you have to find out the P. P is the parasitic delay. Parasitic delay. Parasitic delay means this delay doesn't depend on your process. These are actually a parasite. Like from this point, let's say I am at the Mogbajar. I want to go to Uttara. Okay? I am going from here to Uttara. Now the distance between Mogbajar and Uttara is 15 kilometers. 15, roughly 15 kilometers. Now the speed, that means the velocity of my motorbike is let's say 60 kilometers per hour. 60 kilometers per hour. So how much time I need to go to the Uttara? 60 kilometers, right? So the thing is distance divided by velocity, right? So you need 0.25 hours. That means 15 minutes.
Yes.
15 minutes to go to Uttara. But that was the calculated delay. But there are some parasitic delay as well on top of it. So the parasitic delay will be added. Why? Because you might have some traffic jam. You might have some traffic jam in the Mogbajar signal. You might have some traffic jam in the Bonani. You might have some traffic jam in the airport, right? Those can be there or cannot be there. Got my point?
Yes, sir.
Sometimes they can be there, sometimes they cannot be there. They will not be there. So these are actually parasitic delay. They actually add up. So that's why you need half an hour to 1 hour time to go to Uttara. Even you calculated your delay was, or your time was 15 minutes. So that's why this is the parasitic delay. So what is parasitic delay? I will explain. In different branches, you will see some gates. All those gates will take some time to pass your signal. Those are actually parasitic delay. You cannot do anything about this. Nothing you can do. So these are actually what? Small p1 plus p2 plus p3 dot dot dot. So how many gates you have? It depends on this. Okay? This is parasitic delay. Now you can find the path delay, D. This is the D, not P. D. You can find the path delay. Path delay will be N, small f, plus P. Oh, by the way, what is N? N is number of stages. Number of stages. What is N? Number of stages. What is F? F you have already found out. What is P? P is the parasitic delay. D is the path delay. Now, after that, you have to find out the estimated delay or actual delay. EST, estimated delay. Estimated delay will be D into tau. Now, the value of tau is different for different things. Like tau, the value of tau for inductor and capacitor is 5 RC, right? 5 RL. Remember, for capacitor it is 5 RC. For capacitor it is 5 RC. Now D is D, tau is equal to 3 RC. So for this math it is 3 RC. For capacitor it is 5 RC. So it depends. So this is the value. Now here you have D. Now remember, the B do not have any unit, G do not have any unit, nothing have any unit, no unit, no unit, no unit. R and C, they have unit. The unit of R is ohm, the unit of C is farad. If you multiply ohm and farad, it will give you a second. Okay? It will give you second. So what is the unit of D estimated? Second. Okay? So this is the formula we will be following, and we will find the value, or we will find the, what is that? We will find the estimated delay. Let's go there. And before going there, what is G? G is a formula. G is, okay, let's go there. Let's see. Don't see, do not have to read it. Yeah, here. The G is equal to 1 if it is a NOT gate. G is equal to N plus 2 divided by 3 if it is an AND gate. N is equal to number of input. G is equal to 2N plus 1 divided by 3 if it is an OR gate. Obviously, what about AND gate? AND gate is actually a NAND gate and a NOT gate, right? So N plus 2 divided by 3 plus 1. This is for AND gate. Remember, this is AND gate. What is OR gate? OR gate is equal to NOR plus NOT, right? Now tri-state. Tri-state buffer or a multiplexer is equal to 2, always. It's always 2. So this is the values, this is the formulas. So we'll be using these formulas for finding out the small g's. Now let's go to the math. Here is the math. Here they told you to find out the everything actually. So how can we find out? So let's jump into it. Okay, let's do it. Let's do it. Now at first, what I have to find out? I have to find out the B. B is what? B1, B2, B3, B4, right? So here, how many branches do you have? Here, at this point, you have 3 branches, right? 1, 2, 3. 3 branches, right? So I'm going to write 3 into here. How many branches do you have?
2.
2. I'm going to write 2. Here, how many branches do you have?
2.
2. I'm going to write 2. So how much? 3 into 2 into 2? 12, right?
Yes.
That is your B. Now G. G is equal to G1 plus G2 plus G3 plus G4, right? Not plus, into. So how can you do it? See, like this. So I have to find out the G for these, and these. Only for these, only the path register. You do not have to find out G for these. No, you do not have to. No. Okay? You only have to find out the G for these, and these. So what will be the value of G for this one? Okay, for this one, it is 1. Right? Because it is not gate.
Not good.
Now this is what? This is NAND gate. NAND gate is equal to what? Remember, n plus 2 divided by 3. What is n? N is actually number of input. So 2 plus 2 divided by 3. So how much? 4 by 3. Okay? For this one, what is this? This is NAND gate.
NAND gate.
So again, 2 plus n plus 2 divided by 3. So here you have 3. So 3 plus 2 divided by 3. So how much?
5 by 3.
5 by 3. And again, this is 2 input NAND gate. So this will be 4 by 3. So you do not need these anymore. So we can call it, this is your G1, this is G2, this is G3, this is G4. So can I write like this?
4 by 3.
4 by 3 into 5 by 3,
5 by 3
into 4 by 3 into 1. So your value will be 333, it will be 27. Do not write 9. Do not write 9. Remember, people make mistake. This is not 9, this is 27. So how much it will be? 4 into 5, 20, 20 into 4, 80. This will be 80, right?
Yes, sir.
Okay. Now you have to find out the H. H is C out divided by C in. C out. Which one is C out? C out is this one, the capacitance of the output, right? And C in is this one, 25. Why this is capacitance? Here there is no capacitance, right? But in your next lecture, that means not today, in your next lecture, you will learn about RC delay. That time you will see that this sizing, this is the sizing, the 9x, x, 7x, 6y, this is actually sizing. This sizing will give you an input capacitance. And the value of the capacitance will be the sizing of the capacitance, that is 25. So your output is 65 and your input is how much? 25.
25.
Okay, that is the equal of your input capacitance, 25. So there is your H. Do not make it in decimal. Keep it like that.
Okay, sir.
Now, what is your F? Formula for F was BGH. Right?
Yes, sir.
Your B is 12. G is 80, 27. Your H is equal to 65, 25. The value for that will be 12 into 80 divided by 27 into 92.44. Your value is 92.44. Now the small f. The formula for a small f is what? F to the power 1 by n, right? F is equal to 92.44 to the power 1 divided by 4. Why? Because you have 1 stage, 2 stage, 3 stage, 4 stage. Okay?
Sir,
that's why.
Exactly.
The stage. These are actually your stages, multiple stages. That means how many stages your input has to cross to go to the output. These are actually your stages.
So 3.10, sir.
Okay, right. I'm going to write it. To the power 4 will be 3.10. Now this value has an importance. What is that importance? Let me show you something. For that, I need some more spaces. This value has some importance. What are those importances? Number one, this value must be 2.4, bigger than 2.4 and smaller than 4. No, smaller than 6 actually, not 4. smaller than 6. Okay, this value must be bigger than 2.4 and smaller than 6. So which one is the best? Best is f is equal to 4. If it is 4 or close to 4, the design is much more optimized. Okay, much more optimized. Got my point?
Mhm.
And our design is 3.10. It's okay, no problem. It is between the range and it is almost close to, not almost, it is somewhat close to 4.
Okay.
So that's why we can call it our design is okay. But if it was 4, then our design would have been what? That means the much more optimized. So this is the advantage of this is the importance of this f. Okay. Now come what? Now come to p. P is the parasitic delay. What is parasitic delay? Parasitic delay is the delay for this gate, this gate, this gate, and this gate. There is a table. There is a table for this. Okay, let me show you the table. Yeah, this is the parasitic delay table. See the parasitic delay, parasitic delay. Can you see it?
Yes, sir.
Okay, I'm going to erase some part of it. What is the parasitic delay of this one? See, for different gates, the parasitic delay is different. And for different inputs, the parasitic delay is different. So at first, inverter. For inverter, that means not gate, your input is 1, so your delay is 1. For NAND gate, if your input is 2, delay is 2. If your input is 3, delay is 3. For 4, 4. For N, it is N. For NOR gate, same. 2, 3, 4, N. That means the number of input is equal to number of delay. Now come to the tri-state. If your input is 1, your delay is 2. For multiplexer, if your input is 2, your delay is 4, 6, 8, 2n. XOR gate and XNOR gate, your input is 2, your delay is 4. Because those are actually complicated gates, right? Complicated gates. That's why your delay is more. More complicated gate means more delay. What about AND gate? Delay of AND gate will be 3, 4, something like that. This one will be what? For 2 input, the delay will be 3. Why? Because 2 plus 1. Okay, so 4, 6, 8, something like that. So let's go to our circuit and find the parasitic delay. This one, okay. For parasitic delay, this one is 1. So I'm going to write 1. Here the input is 2, so I'm going to write 2. Here the input is 3, so I'm going to write 3. Here is 2, I'm going to write 2. So your delay is how much? Maybe 5, 6, 8.
Yes, sir.
So your D, that means the path delay, will be N F plus P. So your N is equal to 4,
4.
F is equal to 3.10, P is equal to 8, maybe 20.4, maybe something like that. Something like that. This something will come up like this.
Yes, sir. 20.4.
Okay. 20.4, yes. And this is the delay. Now come to the estimated delay. D estimated
Estimated delay.
will be D into tau, that means 3RC. Now the R and C are given in your question. What was that? How much R and C are given in the question? Okay, 2.5 and 5.5, right? Femtofarad. This is kilo ohm, this is femtofarad, remember. But remember, this is the question, but the example has a different value, 3 and maybe 6. So don't be confused. So what they have done, what this handwritten note is there is a mistake. What is the mistake? The mistake was here the 3 kilo ohm and 6 femtofarad is used. Although the question said 2.5 and 5.5, right? So we will use the 2.5 and 5.5, no problem. We will use 2.5 and
5.5.
5.5. Let's get back. Okay. So D is equal to 20.4.
4 into
3 is 3.
3,
R is 2.5
2.5.
into 10 to the power 3, right? Kilo.
Kilo.
C is 5.5. So write 5.5.
10 to the power 3.
10 to the power minus how much?
3, sir.
Huh?
So it is close to the 10 to the
femtofarad, right?
Yeah.
Femtofarad, how much?
So 4.
Okay, let me give you something. Milli means -3, micro means -6, nano means -9, pico means -12, femto means যে 12 সেমিস্টার হয়ে যাচ্ছে, পাস করে যাচ্ছ।
15, sir.
You do not know. So since we have converted to ohm and farad, so this will be second. Okay, this will be second. So if we calculate these in our calculator, so the value will be 20.4 into 3 into 2.5 into 10 to the power 3
So 8.4
into
5
5.5 into 10 to the power minus 15. So your value is 8.415 10 to the power minus 10. This is a problem. This is a problem means because you cannot convert 10 to the power minus 10 into nanosecond, picosecond, something like that. So what you can do, you can click the ENG button of your phone, no, of your calculator, ENG button. Okay. So if you click ENG button, your value will be like this: 841.5 10 to the power minus 12 seconds. Okay, we can call this 10 to the power minus 12 second into picosecond. We can call it picosecond. Or if you click shift ENG, if you click shift ENG, your answer will be 0.8415
10 inverse 9.
10 inverse minus 9, not 9.
Yes, sir.
Minus 9 seconds. You can call it minus 9 second into nanosecond, right?
Nanosecond.
So this is your delay. So nanoseconds are normally more used than picosecond. So you can call it either way, no problem. Nanosecond, picosecond doesn't matter. Okay?
Yes, sir.
Now we have some few more things to find out, that is X, Y, Z. Remember those X, Y, Z value? Those are actually your puzzle. These are actually done for testing your knowledge, okay, testing your thing. So these are given as a puzzle, so that you can solve it. These are useless things, but these are given as a puzzle so that you can use it. You can find those values, okay, to elongate the math. Now we will be finding out those. How? I'm going to erase this part. And I'm going to draw something else. I'm going to draw a new area that I can find. Okay, now I'm going to find out the value of X, Y, Z. So how to find out the value of X, Y, Z? There is a formula for that. What formula? Remember, at first you have to find out from the output side, that means Z. The formula for Z, that means not Z actually, the whatever inside, whatever inside, 1Z, 2Z, 3Z, you have to write here. Here you have only 1Z, that's why I have written 1Z. The formula will be G into C out divided by small f. That is the formula. G, C out, small f. What is the value of G of this one? Remember we have written earlier. What was that?
1.
1. So G was 1. So I'm going to write 1. What is C out? C out of this one?
Sir, 65, sir.
65.
65.
What is the value of F?
3.10.
So if you put the value here, you will see the value is
83.87.
Okay, let's find out. 1 into 65 divided by 3.10. 83 can also 20.
Oh, sorry, sir.
20.96 or 97. So I can call it 21, because it is sizing, right?
Mm.
This is the value of sizing. You can call it 21. So
21.
if I write it 21, so what I'm going to do, I'm going to do something different. Here you have 9Z, right? Remember 9Z. So I'm going to write 21. Hello? Hello? Hello?
Yes, sir, we can hear you.
Okay. 21. Here you have 9Z. 9Z means 9 into 21, right? So 189. So I can call it, I can write 9 into 21. Okay? 9 into 21. So I have written the value here. Now come the value for 6y. So let's write whatever inside you have. 6y is equal to, again, the same formula, G into C out divided by F. Now, what is the G for this one? 4 by 3. So I'm going to write 4 by 3. What is C out? Now, for that, the C out was 65. But for this, C out will be the capacitor input capacitance of these MOSFET, right? These gates. Here, I told you, for this one, I told you the input capacitance for this is 25. What about these? 21. What about these? 9 into 21, right? So since they are parallel, they will be added. So for this one, output capacitance is the input capacitance of these two. So 21 plus 9 into 21. Okay, divided by 3.10. So here, if you do that, the value will be
21.
4 by 3 into 21 plus
So
9.
90.32.
3.10. Okay, 90.32.
32.
32. Do not round it up. Divide by 6. So your y will come out. Your y will be 90.32 divided by 6. Okay, by 6. The value is
15.05.
Okay, I can call it 15. I can call it 15. So I'm going to write the 15 here. But before that, let's make them disappear. Here it was 6y. It is 5y. Right?
Mm-hmm.
Okay. You can write directly, or you can write 5 into 15 and 6 into
15.
Or you can just multiply and write it. Your wish, no problem. Next one is 9x. Again, the same formula. G into C out divided by F. What is the G? G is 5 by 3.
5 by 3.
What is C out? C out is these two because they are connected, right? Divided by 3.10. Now, if you find the value 5 by 3 into 6 into 15 plus 5 into 15, so 3.10. The value is 88.71. 80. Do not round it up. Do not round it up yet. Divide by 9. So your x will be 9.85. 9.85. Now round it up. Make it 10. Okay. So your x is 10.
10.
I'm going to give you some marking. Your x is 10. Your y is 15, and your z is 21. That is the complete math. Remember, one of these math will come in your exam. Maybe I will give you different values so that you cannot copy. Okay?
Okay, sir.
Understand?
Mm-hmm.
So one of our big topic is done. Now I'm going to stop here. So I suggest you to see the video that I'm going to upload after the class and come up with some questions maybe. You can ask me the questions. I can, and then I will answer the questions in the next class. And since we have one more big topic, I was hoping that I could finish that today, but not today. No, maybe I cannot. Here the logical, not the logical CMOS processing. Here the CMOS processing, the PPT 0.07, that we will learn tomorrow. There is the CMOS fabrication. Here you have CMOS process, CMOS structure. The thing I have already talked about in the lab class, that is here. Okay, all the writings are there as well. These are the process, but this is the mask layout. Remember, I told you the mask layout doesn't matter. So if you design, if you give the N well first, or design it on N well, or if you give the N well later, doesn't matter, because you as an engineer will make these. This is the layout. As an engineer, you will make these. But whoever making the wafer, they will deassemble your design into parts. Okay? Here they will click the N type. Here they will click the what is that, polysilicon. Here they will separate the N diffusion. Here they will separate the P diffusion. Here they will separate the contact. Here they will separate the metal. By separating those, then they will apply. Okay, so your job will be making these. So which one you will do first doesn't matter. Got my point?
Yes, sir.
They will separate those and they will apply. So tomorrow, maybe inshallah, we will learn about the lithography process. This is a very big process, but easy process. Okay, easy process means easy to understand process.
Yes, sir.
And this is a theory, not anything to do with maths or anything else. So just a theory. Got my point?
Yes, sir.
Okay. So there are. So this is a PPT file. You can. I'm going to upload this now. I'm going to upload it to your group right now. Okay, so that you can see this one logically for this logically for. Okay, I have uploaded. You can see those. Okay, so I think I'm going to stop the recording.